All right, let's dive into a genuine cosmic mystery. We're playing detective today, but our clues are smaller than anything you've ever imagined. We're going deep inside the atom's core to solve what I'm calling the case of the missing mass. So here's the central puzzle, the question that kicks off this whole investigation. Imagine you're building a model. You weigh every single piece before you start. But then, when you put the finished model on the scale, it weighs less than all the parts you started with. How is that possible? Well, believe it or not, that's exactly what's going on inside every atom, and we're about to find out why.
Okay, first stop, let's go to the scene of the crime. Or, well, the scene of the mystery anyway, the atomic nucleus. This is where all the protons and neutrons, what we call nucleons, are jammed together in a space so tiny it almost doesn't make sense. To really get a feel for this, just look at these numbers. The nucleus, which has nearly all the atom's mass, is about 100,000 times smaller than the atom itself. You know what that's like? It's like putting a single pea in the middle of a massive football stadium. The rest is just empty space. And this is where it gets really weird. You've got all these protons, all with a positive charge, crammed into that tiny, tiny space. Now, Basic Physics 101 tells us that like charges repel each other. So the nucleus should be this unbelievably unstable, explosive thing, right? It should just fly apart. But it doesn't. So what in the world is holding it all together?
The answer, our first major clue in this case, is a force so powerful it gets a very fitting, very simple name: the strong nuclear force. Think of it as the universe's most powerful superglue.
This is it. This is the force that wins the tug of war inside the nucleus. It's this incredible attraction that works between protons and protons, neutrons and neutrons, you name it. It's kind of like the bouncer at a chaotic club, making sure nobody gets out of line. But here's the catch. This force is like a world champion boxer who only fights inside one very, very small ring. Inside the nucleus, it's overwhelmingly powerful, easily beating the force that's trying to push the protons apart. But the second you step outside that tiny range, poof, it's gone. Its power drops to pretty much zero. It's all powerful, but only at point-blank range. To really appreciate just how strong this force is, let's talk about density. You know, water is our baseline, 1 gram per cubic centimeter. Iridium, one of the densest things we can find here on Earth, is about 22.6. Pretty heavy stuff, right? Well, that's absolutely nothing compared to a nucleus. The average density of an atomic nucleus is 180 trillion grams per cubic centimeter. That number is so big, it's hard to even wrap your head around. To put it in perspective, if you could crush the entire planet Earth down to that density, it would be small enough to fit inside a city park. That's the mind-boggling power of the strong force at work. Okay, so we've established that this force is insanely powerful. But a force that strong needs a huge source of energy. Where does it come from? Well, to figure that out, we have to do what all good detectives do: follow the money. Or, in our case, follow the mass. Let's look at the evidence, using a helium-4 atom as our guinea pig. It's simple: 2 protons, 2 neutrons, and 2 electrons. We know how much each one weighs in atomic mass units, or AMU. So let's just add them all up. A little quick math, and we get an expected total mass of 4.0331 AMU. Simple, right? But here's the big twist. When scientists actually measure the mass of a real helium-4 atom, they don't get that number. The actual measured mass is 4.0026 AMU. It's lighter. The whole is literally less than the sum of its parts. Something is missing. And there it is, our smoking gun. 0.0305 atomic mass units have just vanished. Poof, gone. This difference has a name. It's called the mass defect, and figuring out where this mass went is the key to cracking this whole case. And the solution comes from maybe the most famous 3 letters and a number in the history of science, from Albert Einstein himself: E equals mc squared. What it tells us, fundamentally, is that mass and energy aren't separate things. They're 2 sides of the same coin, and you can convert one into the other. And just like that, the case is cracked. The mass was never really missing at all. When all those protons and neutrons smash together to form a nucleus, a tiny little bit of their mass gets converted into a huge amount of energy. We call that the nuclear binding energy. It's the energy that fuels the strong force. So that missing mass isn't missing. It's the energy that's gluing the entire nucleus together. So now that we've solved the mystery of the missing mass, we can use this knowledge to understand something even bigger. What makes some nuclei super stable while others are radioactive and fall apart? Turns out there are rules. There's a blueprint for building a stable nucleus. Take a look at this. This chart is basically the master list of every nucleus we know of. It's called the band of stability. If you're a nucleus inside that narrow blue band, you're stable. You're good to go. But if you fall outside that band, you're unstable and radioactive. And you can see a clear trend, right? The little guys, the light elements, they like a nice, clean one-to-one ratio of neutrons to protons. But as they get heavier and heavier, they need more and more neutrons to add extra strong force glue to keep all those protons from repelling each other. And check this out. There's another really cool pattern in the data. Nature seems to have a favorite number, 2. Or at least it loves even numbers. Nuclei that have an even number of both protons and neutrons are way more likely to be stable. Look at that, 157 of them. Now compare that to nuclei with odd numbers of both. There are only 5 stable ones in existence. Just 5. And then it gets even cooler. There are these things called magic numbers. Just like how electrons fill up shells and create super stable noble gases, it seems protons and neutrons do something similar. When a nucleus has a number of protons or neutrons that hits one of these magic numbers, it's extra stable. And if it has a magic number of both, like our friend helium-4 with 2 protons and 2 neutrons, it's called double magic, and it's rock solid. Okay, so we've got all these patterns, these rules of thumb, but can we actually measure stability? Can we put a number on it and find out which nucleus is the most stable of them all? To do that, we got to go back to that binding energy we discovered. The key measurement here is the binding energy per nucleon. It's a simple idea, really. You take the total binding energy, that energy from our missing mass, and you just divide it by the total number of particles in the nucleus. What you get is a score for how tightly bound each particle is on average. The higher the number, the more stable the nucleus. And this comparison tells the whole story. Helium-4, our double magic example, is really stable. It's got about 7.1 mega electron volts of energy holding each particle in place. But look at iron-56. It's even higher, up around 8.8. So this shows us that stability isn't just a straight line. It kind of goes up and then peaks somewhere in the middle of the periodic table. And that peak is right around mass number 56. Iron-56 sits right at the top of the stability mountain. It's one of the most tightly bound, most stable things in the entire universe. And this isn't just a fun fact. It has huge consequences for stars. A star spends its life fusing lighter elements together, climbing up this peak and releasing energy. But once it starts making iron, the party's over. You can't get any more energy out of iron. In fact, it costs energy. That's the end of the line, and it's what triggers a supernova. Which brings us right to our final thought for the day. We solved the case. The missing mass was actually converted into the energy that binds the atom together. So here's the question I want to leave you with. If turning a nearly undetectable amount of mass from a single atom into energy is powerful enough to do all that, what happens when we apply that same principle on a massive scale? What does this incredible power source, this conversion of mass into pure energy, actually run in our universe? From the sun that warms our planet to the power plants that light our cities, it's all right there, in the case of the missing mass. Thanks for joining me on this one.